we were talking about the solubility rules, and now we'll learn how to apply those rules to what are called precipitation reactions. You've probably heard of hard water. Maybe wondered, how is water hard? It's a liquid, right? When they say hard water, they mean water that contains ions, such as calcium and magnesium. There are other ions as well. And what happens then is that those ions in the water can react with things like soap, and that leads to a bathtub ring after taking a bathtub. It also leads to, if you have water that evaporates, droplets on the shower walls and stuff, it'll leave little white spots behind, and that's the minerals that were dissolved in the water. So this soap scum would be getting on our clothing when we wash it, because all soap is going to react with calcium and magnesium and cause this. So what most laundry detergents contain is something like sodium carbonate. And what sodium carbonate does is the carbonate in it will react with those ions like calcium and make an insoluble compound, calcium carbonate. It also reacts with magnesium to make insoluble magnesium carbonate. And so it causes those ions to come out of the solution, and so then they can't react with the soap and leave this soap scum or curd on your clothing. A precipitation reaction is one in which we have a solid forming. Solids that form in this way are called precipitates because they precipitate in the solution, much like meteorological precipitation, like snow or rain falling from the sky. So here I'm mixing two clear, colorless solutions. It looks like we're mixing water and water, and we have like yellow snow appearing, right? We have this solid appearing. This is a solid that's formed when two solutions are mixed. It is a precipitate, and that will fall to the bottom. So in this example, we have potassium iodide, which is soluble, and lead nitrate, which is also soluble, in these two solutions. And when we mix them together, then the potassium ions can encounter the nitrate ions, and the lead ions can encounter the iodide ions. And what we observe is that the lead and the iodide will form a precipitate. If we look at the solubility rules, we see that iodide compounds are generally soluble except when lead 2 is involved. And so the solubility rules predict that this would happen. So we're going to learn how to predict whether a precipitation will occur, and if so, what those compounds are. And what we're doing here is we're looking at the ions in the original compounds. So one of them had potassium and iodide, the other had lead and nitrate. This is one of my favorite analogies. I've mentioned before that I think of the metals as being masculine, and here they're actually blue right here, and I think of the nonmetals as being non-masculine or feminine, and so these are pink. And just to be clear, this has nothing to do with gender roles or anything like that. This has everything to do with opposites attracting, opposite charges attracting, and a way to help you make sense of what's going on, a way to relate it to something that you're familiar with in regular life, right? So I think of potassium and iodide as a guy and a girl, and they're going together to a party. This party happens to occur in a beaker, but they're going to the party and they're going to mix and mingle and meet new people. And then we also have lead and nitrate. So lead is the guy, nitrate's the girl. They're going to go to the party as well, and they're going to mix and mingle. So potassium now is going to meet up with nitrate. And it's like, oh, hi, nitrate, nice to meet you, la-di-da, right? But then lead meets up with iodide, and this is one of those movie moments where it goes slow-mo, right? And their eyes meet across the crowded room, and they're just like, oh, right? instant chemistry, right? And so these are the people that you don't see them the rest of the night. Where are they? Well, they're out on the back porch making out the whole night, right? Because they're just like so attracted to each other, right? They've become a unit almost, right? They're together, right? So this is just to help you remember or make some sense out of what's going on here. So the way we predict precipitation reactions is we look at the ions, the cations and the anions that come in, and we try switching the partners and see if those make insoluble compounds. Okay, so the way we predict, well, is lead iodide going to be an item, or is potassium nitrate going to be an item? Is it going to be a solid? We use the solubility rules. Okay. You can mix two solutions of ionic compounds and not get a precipitation. Just like you can have a party where nobody falls in love with anybody else. You have a great time, but no relationships are formed, right? No chemistry happens. So in this example, we have potassium and iodide and sodium and chloride. And when these guys mix and mingle, sodium's like, oh, hey, iodide, yeah, whatever. And potassium and chloride are like, you know, it's not like they hate each other or anything, but they're not going to like go off and spend the rest of their lives together, right? So then what has happened? Well, there's no chemical reaction that has happened here. Nothing new has been formed. Something is different. It's a physical change. These two solutions have mixed. So it's just a physical change, but there's no chemical reaction. And so there's not really a chemical equation that we can write, because we still just have potassium and iodide ions in aqueous solution and sodium and chloride ions in aqueous solution. And if we think back to that solubility, list of solubility rules, let's maybe just go back there real quick. Up here at the top, lithium, sodium, potassium, and ammonium, compounds containing those ions are soluble with no exceptions. What this means is that lithium, sodium, potassium, and ammonium are extremely commitment phobic. They do not get into relationships with anions. They just don't, right? They're never going to form precipitate. And there's some nonmetals. Some of the anions also do this, nitrate and acetate. Not going to get in a relationship with anybody. So they're never going to be part of a precipitate. The rest of these guys, it just depends on who else is there. They're going to precipitate with some ions and not with others. So this is a slide showing guidelines for how to write equations for precipitation reactions, and this is a skill that you will need to demonstrate on an exam. I'll talk through this real quick and then we'll do some examples. First, we're going to write the formulas for the two reactants, and then we're going to look at the formulas of the products that could possibly form, and then we're going to refer to the solubility rules to see if either of those products is going to be insoluble. If both of those probable compounds are aqueous, if they're soluble, then no chemical reaction has happened, and we just write no reaction. We always kind of hope that this is the kind we're going to get because it's a lot less work than if there is a chemical reaction. If any of those products are insoluble, then we're going to have to write the formulas for the products. We're going to have to indicate whether those products are solid or aqueous. Solid, the S here is for solid, S is not for soluble. This is a solid, it's insoluble. The aqueous compound is soluble, and then we balance the equation. So let's do some examples. Write an equation for the precipitation reaction that occurs, if any, when ammonium chloride and iron 3 nitrate mix. So what we're going to do is we're going to start out by writing the formulas for the reactants. These are ionic compounds, and so we need the formulas for the ions. So the first compound is ammonium chloride. So ammonium is a polyatomic cation, and we just need to memorize that it is NH4+. chloride is an anion. The nonmetals make negative ions. And so this is the chlorine, and we predict its charge based on its position in the periodic table. If you haven't solidified this in your mind yet, now would be a good time to do it, because we're going to keep doing this. It's not going to go away. And then we've got iron 3 and nitrate. So the symbol for iron is Fe. And what does the Roman numeral 3 tell us? That's the charge on the ion. It's not how many are in the compound, it's the charge. So this is Fe3 plus. And then nitrate, that's another one that we have to memorize, NO3 minus. So we're going to write the formulas for the reactants, and we do this by looking at the ion formulas with their charges and getting the correct number that they will make a neutral compound. Right, so here we have a positive 1 charge and a negative 1 charge. If we have one of each of those, NH4Cl, we'll have a neutral compound. And what is the state for ammonium chloride? Is it aqueous or solid? It's going to be aqueous. Precipitation reactions, it doesn't specifically say it in here, and it should. Precipitation reactions, we're always looking at solutions mixing. So this should be called aqueous. And then iron and nitrate, different ways to think about it, but we should all come to the same conclusion that we need 3 of these nitrate ions to balance the 3 plus charge on the iron. And so we would write that as Fe, NO3, 3. And that one's also going to be aqueous. Okay? Now we're going to see what happens when we change partners. So ammonium came in with chloride. We know there's no chemistry going on there. So let's see what happens when ammonium meets nitrate. So I'm going to write those two next to each other, the formulas for their ions. And then I'm going to look at the other possible combination, which is iron and chloride. In the formulas for ionic compounds, it's always the cation first and then the anion, just because that's how we decided to do it. So I'm going to write Fe3 plus first and then the chloride. Now, would it be any different if I wrote this one over here and this combination over there? No, that's the same, because this is adding, right? 1 plus 2 equals 3, 2 plus 1 also equals 3. The order doesn't matter when you're adding. So now what we need to do is identify, well, is this compound going to be soluble? Yeah, question. Yes, the cation. And so, like I mentioned before, I think of the cation as being the guy. And so if you think about like a formal invitation to a party or something, Mr. and Mrs., right? They never say Mrs. and Mr., right? Why? Well, it's just how people decided to do it, really, okay? So always the metal and then the nonmetal. So would these two form an insoluble compound? Well, if you look at your table of rules, on that first line, you're going to see that ammonium compounds are always soluble, no exceptions. So this is going to be aqueous. If you go to the second line, you see that nitrate compounds also don't form any insoluble compounds. Well, what about iron and chloride? So if we go down a little bit further, we see iron, chloride, bromide, and iodide. Those are also mostly soluble. There are a couple of exceptions, but iron is not one of them. So this is also a soluble compound. So then there's no chemical reaction that occurs. So we could write no reaction, or we'll even get lazier than that, and we'll write capital N, capital R, no reaction. And we're done with that one. Any questions? Let's do another one. Write an equation for the precipitation reaction that occurs, if any, when sodium hydroxide and copper 2 bromide mix. So again, I'm going to start by writing the formulas for their ions. So I've got sodium ion, and we've gone over how you write these ions. So that's Na plus because it's in group 1A. Hydroxide is OH minus because you memorize it. Copper 2 is Cu with a 2 plus charge. The Roman numeral tells us the charge. And then bromide is Br minus. So I'm going to put these together, sodium and hydroxide. And when I put the copper and the bromide together, I'm going to need 2 of the bromides. Both of the reactants here are going to be aqueous. If you're not sure about that, you can look them up in the table of rules. And then we're going to swap partners. So we're going to see, well, what if we've got sodium with bromide? Let's write those two next to each other and see if any sparks fly. And we've got hydroxide and copper. We've got Cu2 plus and OH minus. And before I bother to write formulas for those products, I'm going to check to see if they're soluble or not. Because if they're all soluble, then I don't need to bother. Well, sodium and bromide, is this going to be soluble or insoluble? Soluble, because if I look at the table, sodium compounds are always soluble. Sodium doesn't form insoluble compounds, just doesn't. At least not in Chem 1A. How about, so I'm going to write AQ down here just to remind myself. What about copper 2 and hydroxide? Insoluble. We have to go down the table till we get to the bottom half where compounds are mostly insoluble. That's where hydroxide is. There are some exceptions, but copper is not one of the exceptions. And so this is going to be a solid because this is not going to be soluble. So now we have to finish. So I'm going to put the sodium ion and the bromide ion together to form a compound. And then I'm going to form a compound with the copper and the hydroxide. And it didn't leave much room there. We learned how to write these ions. We learned how to write these formulas in a previous chapter, right? And so if you still haven't mastered that, this would be good to work on and master it because this is one of those things that's not going away. We're not going to be calculating average atomic masses from percent abundance and individual isotope masses, except there might be one question on the final. That's something we're not going to do again. But this ions, writing the compounds, stoichiometry, dimensional analysis, those things are just going to keep coming at us. So I've got my compounds for my reactants and my products, and now I'm going to balance the equation. So here I've got one sodium and one sodium, so that's all good. And the hydroxide is a polyatomic ion, and it stays together. I've got hydroxide here, and I've got hydroxide over there, so I can balance that as a unit. I've got one hydroxide over here, and over here I have 2 hydroxides. So in order to balance that, I can put a 2 in front of sodium hydroxide. When I put a 2 here, now I messed up the sodiums that I just balanced. So let's take care of that before we forget about it. So I need to put a 2 here. So now I have 2 sodiums and 2 hydroxides on each side. So now I can move on. I'm going to look at copper. There's one copper here, and there's one copper there. And then bromides. I have 2 bromides and 2 bromides, and there's my balanced chemical equation. Any questions? So we're taking all these pieces that we learned earlier in the semester, now we're putting them together.